Okay. So we continue with our lectures on graph theory. Today we are going to discuss what is called acyclic graphs in the first part. So what is an acyclic graph? As the name suggests, a graph that does not contain any cycles. So they are called acyclic graphs. Or a more commonly used word is a forest. So acyclic graphs are called forests. Now, so here is an example of a forest. If you want to look at this, so you can see this graph represented below does not have any cycles in it. So all the all the components of a forest are called trees. So components are the maximal connected subgraphs, right? If you remember. So you can see that there is this one component. Then there are these two single vertices, the 17 and 16 are components. Then there is this path on three vertices, which is another component. And then you have a vertex with several neighbors. This is another component. And there is a path again on four vertices. Right? So these are all examples of trees, and that together form an acyclic graph, which we call a forest. Okay, so here we have a forest. Now there is a special name for the this type of graph where we have one central vertex and every other vertex is a neighbor. Such a tree is called a star. And stars are also some important class of trees we will see sometime. Now, so this is an example of cyclic. Now, here is one theorem. Suppose you are given an acyclic graph, let's say F, okay? And assume that this forest has at least one edge, and you can have just isolated vertices. But apart from that, if you have just a graph with at least one edge, then this forest has at least two vertices of degree exactly equal to 1. Okay? So the vertices of degree 1 are called leaves. So in a tree, if you have a vertex of degree 1, they are called leaves of the tree. So how do you prove this theorem? Okay? So you want to show that given an acyclic graph with at least one edge, it contains at least two vertices of degree exactly equal to 1. Now, maybe you should think about this for a few minutes. It's very easy to come up with a proof. But there are several ways to do this, but here is one. So, we already looked at this kind of extremal questions. So, take any non-trivial component of the forest and then consider a maximum length path in that. So, whatever is the longest path. So take given any graph, what you do is that you look at the longest path in this graph, and then we look at the endpoints of this. Let us say u and v. Okay. So you have this path uv, which is a maximum length path in one of the components, right? Any component that you are taking, and then look at the n vertices u and v. We are looking at non-trivial components, so there is at least one edge. Now, what can we say about the degree of u? Okay. So I claim that the degree of u cannot be more than 1. I mean, it has to be exactly equal to 1. So why is this? So if you look at the vertex u, suppose it has any other neighbor, right? If it has any other neighbor, let's say u dash, the vertex u dash cannot be outside the path, because if it is outside the path, we can get a longer path by starting from u dash to u, right? And then continuing on the path. So this will give me a longer path, but we started with the maximum length path. Right? So therefore, you cannot have any other neighbors. I mean outside the path. Now, if it has a neighbor inside the path, right? Then what does it say? Suppose this neighbor of you is inside the path, then you have some neighbor in the path. Then you already have the connection between these two vertices along the path UV, and then you have this additional which creates a cycle. But we started with the assumption that the graph is acyclic. So therefore, this is also not possible, which says that the vertex u must have degree exactly equal to 1. Now the same argument holds for v, so therefore u and v must be vertices of degree equal to 1. So this is true for any maximal path, so therefore we can show that the tree contains at least, any non-trivial forest contains at least 2 vertices of degree exactly equal to 1. Okay, so and this of course holds for we proved it for just a single tree, any non-trivial tree. So if there are several components, then you can say that there are several leaves in the tree, right? Okay, so here is the proof. Let F be an acyclic graph and T be a non-trivial component. Now consider a path of the maximum length in T, say P is equal to U1 to UK. Every neighbor of U1 is mentioned, and of course UK also lies on the path P, right? Because otherwise we said that there is a longer path. Now if there is a neighbor which is other than the immediate neighbor in the path, then there is going to be a cycle, so therefore the graph is acyclic. I mean, therefore the vertices have degree 1 because the graph is acyclic, right? Okay, now here are here is a homework question. Show that the following are equal. So this is a very important result in the study of cyclic graphs. So these are the statements. Okay, first statement is that T is a tree. Okay, so given a graph T, right? The graph T is a tree. That is equivalent to the statement that there is a unique path between any two vertices of the graph T, and they are also equivalent to saying that T is a connected graph, but T minus E is not connected for any edge E in the graph. Okay. So for every edge, T minus E is disconnected, but T itself is connected. So in this sense, we can say T is minimally connected. So if the graph is minimally connected, then it must be a tree. And the graph T is acyclic, right? There is no cycle. But if you add any edge, right, which was not present, right? So suppose U and V are not adjacent, you add an edge U to V, then it creates a cycle in the graph T. If this is true for every non-edge U and V, right? So if UV is non-edge, you add it to it, it creates a cycle. If that is true for every non-edge, then we say that is also a tree. So these are all equivalent. So we have to show that let's say something like 1 implies 2, implies 3, implies 4, implies 1. So whichever way you want, you can show this, but show that these statements are all equivalent. So the proposition is as follows: a connected graph of order n, which means the number of edges is n, is a tree if and only if it has n minus 1 edges. Okay? So we are given that like the graph is connected, which means that any two vertices, there is a path connecting them, and it has exactly n minus 1 edges. Right? Now suppose we have a tree. Okay, so we have to show two things, right? Suppose that the given graph is a tree, then we have to show that it has exactly n minus 1 edges, and we have to show that if a connected graph has exactly n minus 1 edges, then it is acyclic. Right? That is what we want to show. So here is the proof, right? So let us first show that. Let us first show that if the graph is a tree, then it has exactly n minus 1. So so because it is a tree, of course we know that it is connected, right? Now let us take an n vertex empty graph without any edges, right? And then add edges one by one. Now, what happens when I add an edge? When I add an edge, if I take two distinct components, two different components which are not connected by an edge, and put an edge between them, then these two components, because so each component, for example, I have this component and this component, right? If I take any vertex here and any vertex here, and then connect them with an edge, okay, then what happens? This entire thing becomes a component, because in this component I can go from any vertex to any other vertex because there is a path, right, by definition. And similarly from this vertex, let's say this is x and y, then from y to any other vertex in this component I can, right? Now, to find a path from any vertex to any vertex in this big part, all I have to do is that take a path from the starting vertex to, let's say, u, then take the edge u to x and x to y, and from y to any other vertex that we have here. Right? So this should give as a path between any two vertices. So therefore, if I take two distinct components and put an edge between some vertices of these two, then I will get a connected larger component. Right? So this is which says that if I add an edge between two distinct components, the number of components decreases by exactly 1. Right? And of course, it cannot decrease by more than 1 because an edge only can connect two components. So if I start with n vertices, then when I add one edge, it can reduce the number of components by 1. Right? So I start with exactly how many components? N components. Then I add one edge, it decreases the component by 1. Then I add one more edge, right? It decreases the components again by 1, right? If I am connecting two distinct components. Now, if I add an edge between the vertices of a component, it will not decrease the number of components. So but it will create a cycle, right? So for the time being, let us not add such an edge, right? And let us see that we just keep on increasing the edges so that the number of components decreases every time. Now, if I do this, right, to maximize the and minimize the number of components, then because I start with n components, I need to add at least n minus 1 edges to make the graph connect. Right? So every time I add an edge, it only decreases the number of components by 1. So I start with n, then n minus 1, n minus 2, etc. If it becomes 1, then I have added at least n minus 1 edges. So before adding n minus 1 edges, we cannot make the graph connected. So we need to have at least n minus 1 edges. Now, can we have more than n minus 1 edges? Right? So at least n minus 1 edges are required to make the graph connected. But suppose you add one more edge, right? So if the graph is already connected, and then you add edge between vertices of some component, then you automatically create a cycle because there is distinct path between two disjoint paths between these vertices, the edge and the path in the original. So therefore, that is not there. Right? So therefore, we see that if the graph is a tree, which means that connected and acyclic, then it has exactly n minus 1 edge because it cannot have more than n minus 1 edges, because once it becomes connected, you cannot add any more edges. And to become connected, you need even we can make it more precise if you want. Now, here is another observation that is something that we defined earlier, but we can define in a different way. Okay. So we define a rooted tree, right? In the earlier case when we look at functional diagrams, we define rooted trees are trees where there is exactly one cyclic vertex. So those were called the roots, and then we had the rooted tree as this functional diagram. Now we can also give a rooted tree by the following. We have an undirected graph, and you just make one of the vertices as special vertices, okay, and call it a root. That becomes a rooted tree. Okay, so this is the natural or the first way. I think people are coming with the notion of rooted trees, because you take a tree and then consider one of the starting vertex or initial vertex or special vertex, which we call root. Okay. So you take any arbitrary tree, pick any vertex and make it a special vertex, say that this is the root. So that becomes a rooted tree, right? We can start from a vertex and pick any of the vertices to make root. So there is this graph that we get, right? This is a rooted tree where this vertex is special, right? And instead, I take this same graph and make this a special, then I get another rooted tree. Now, there is a one-to-one correspondence between the rooted trees that we come up like this and the functional diagram which is rooted. Because we observe that in the functional diagram, if you have a cyclic vertex, then every path from other vertices must lead to this vertex. It should all be coming into this, because this vertex already has an out degree, right? So it cannot have any other incoming edges, outgoing edges. So therefore, every edge to it must be incoming. Now, because of this, this vertex, its neighbors also must be incoming edges, right? So we can follow this argument and show that once you fix a root, right, then all the paths must converge to this cyclic vertex or the root. So that is how we get the functional diagram. Right? Now, so that rooted tree is exactly equivalent to this, because all you are doing is that, okay, whatever is, once you finish the root, every path converges, right? Basically, from every leaf, you go find a path to this vertex, which is directed path. So, because that is a unique way to do it, we see that there is a bijection between these. So therefore, we can now call any of these as rooted tree without worrying about which definition it comes from, and we can use it as it is, and we can go from one to the other and etc. So this is a simple observation. Now, what are the main questions that we are interested in combinatorial? It's of course counting questions. So here are some natural counting questions that arises. Of course, there are many more. I just mentioned a few, right? So one question is that what can we say about the number of trees on the vertex set V, let's say. So given a vertex set V, want to Vn, we want to see how many distinct trees you can make on this, right? So with the label we want to Vn. Now the number of trees, let's say that where each vertex a degree is now specified. Let's say Vi has a degree exactly Di, right? V2 has degree exactly D2, etc. Now in this case, can we count the number of trees? Or if you say that the number of non-isomorphic trees on n vertex, because when you have labeled trees, there could be isomorphism between the corresponding trees, some of them, right? So if there are isomorphisms, when we don't want to count all of them, we want to just say how many trees are there which are equivalent under the isomorphs, right? I mean, distinct under the isomorphs. So how many classes are there, right, under this equivalence relation of isomorphs? So that is another question one can think about, right? You can ask number of rooted trees, number of acyclic graphs, right? All this we can ask about just the acyclic graphs. So these are all questions. Some of these we will try to tackle now, and some of these we can try to work out when we look at further topics like maybe the species and things like that. We might find an easier way to do this. But we will look at a couple of things at the moment. Now, here is one of the questions, right? So, so what was this question? That the number of trees with degree of vi is equal to di. So here is a theorem which explains or counts this. So number of trees on the vertex at v, where degree of vi is equal to di, is given by n minus 2 factorial over d1 minus 1 factorial. I think there is a missing into dn minus 1 factorial. Okay, so d1 minus 1 factorial, d2 minus 1 factorial, etc. dn minus 1 factorial, where the summation di is equal to twice the number of edges. We know that, right? The total degree is twice the number of edges, and therefore that must be equal to 2 into n minus 2, because the tree has exactly n minus 1 edges. So therefore, here is the formula that given a vertex at v1 to vn, and given that every vertex vi has degree is equal to di, we can construct trees only if, of course, summation di is equal to n minus 2. Otherwise, we cannot do that. And if this sum is equal to 2n minus 2, then the formula is given by n minus 2 factorial divided by d1 minus 1 factorial into d2 minus 1 factorial plus dn minus 1 factorial. Okay, so now how do you prove this? Okay, so here is the proof. So what we are going to do is to use induction on n. So the base case, n equal to 1 is trivial, because there is no edge, there is one tree, and that's it. You can see that the formula holds. And for n is equal to 2, again there is a unique tree, right? What is the unique tree? The single edge, right? That is a tree. And this happens precisely when d1 and d2 is equal to 1. And in the other cases, right, d1 is equal to 2 and d2 0, we can see that there is no tree, right? This is something that you can immediately see. So therefore, again we can see that the formula holds. You just verify this. So once you have the base cases, let us assume that n is at least 2. N is strictly greater than 2. We have proved 1 and 2. And now suppose the result holds if the number of vertices is less than or equal to n minus 1. Right? So if the number of vertices is strictly less, then it holds. Now, what we do is that we take the set of trees on the vertex set v1 to vn with the degree of vi is equal to di. So collect all this, right? So given this sequence d1 to dn with the degree of vi is equal to di, we look at the set of all trees that we can construct on the vertex set v1 to vn with this property. Okay. So consider the set and call it as x. Right? So we can observe that the di cannot be 0 for any n, right? Because we are talking about trees, and because it is connected, like this is one way to look at this, right? We cannot create any tree if di is 0 for some right? Because it cannot be connected. As far as we are not looking at the trivial tree where n is equal to 1. We are assuming that n is strictly greater than 2, right? So therefore, we can think of this and say that, okay, now di cannot be 0 because the graph is going to be, so there is no tree possible. So if di is 0, we will see that, like, in this formula, right, we will get di minus 1 factorial. That becomes a problem in our definition, so therefore it doesn't make sense. So we will say that that is not possible. Right? So therefore, di is equal to 0 is ruled out. Now, so suppose dj is equal to 1 for some j. This we can always assume. Why? Because suppose for every di, right, was greater than or equal to 2, then we have n di's, right? So therefore the sum is going to be equal to 2n. I mean, it's greater than 2n minus 2. Right? If every vertex has degree at least 2, there are n vertices. Total degree will be more than 2n. So therefore we know that since di is not non-zero, it must be equal to 1 for some vertex. So let us say dj is the vertex whose degree is 1. There's at least 1. Okay? So let us fix this particular vertex dj whose degree is going to be 1. Now what we notice is that, like, by the definition of the way we construct this, right, d of vi is equal to di for all the graphs in X. Right? So which means that for the graph that we are going to consider in X, the degree of Vj is going to be always 1. Right? So Vj is going to be a leaf in all the trees in X. Okay. So what we can see is that all the trees that we are considering, Vj is always going to be a leaf, which means that it has exactly one neighbor. Right? Now we collect these neighbors, right, and then make another set like this, right? For every tree in A, that AK is the set of all trees such that Vj Vk is an edge in the tree, right? Because Vj has a unique neighbor, it is going to be exactly 1k for a given tree, right? So that k, it will be different from j because there is no loop in our trees, right? So therefore, for every case, we can consider the possible case, right? So AK is basically the set of all trees such that Vj Vk is in the edge of T, right? So so we are basically now collecting with the index of the neighbor of this particular vertex Vj. That could be different in different trees, right? But of course, the degree of Vj is actually equal to 1, but the neighbors could be different in each of the different trees. Now, because we, this AK must cover, right, all of A in at least some of these cases. A is going to be disjoint union AK, and this is disjoint union because you cannot have two different cases intersecting, right? Because there is a precisely unique neighbor for Bj. So therefore, we get a disjoint union of AK, which is equal to A. Now, let us pick some K which is different from J, of course, right? So, so what we do is that we are going to delete this single degree vertex, which is a leaf, right, Vj. Once I delete the vertex Vj, what happens, right? Because it's a leaf, it is not connected to anything other than its unique neighbor. And every path from this vertex, because the tree is connected to every other vertex, is actually going through the neighbor, right? So if I remove this particular leaf, the remaining graph is still going to be connected. It's something that you can immediately see from the structure of a tree. Right? If you remove the leaves, it does not affect the connectivity of the remaining part. So therefore, we are going to get trees on the vertex at v minus vj. Right? So v1 to vj minus 1, then vj plus 1 to vn. Right? So on n minus 1 vertices, we get trees which are again connected. And what is the property of the trees that we obtain this way? For all the trees, degree of vi is equal to di, right? Because we have not changed the degree of anything except for vk, right? So for I not equal to k, degree of v is actually equal to di. Now, once you, right? So once you observe this, what happens to degree of vk? Degree of vk changes exactly by 1, right? It reduces by 1. because we just removed one of its negatives. So it is going to be dk minus 1. Right? Now we can see that there is a bijection between the trees AK that we are looking at and the set of trees that we obtain here by deleting this, because we precisely have the same thing here except we removed one leaf. And if you have anything here with this degree sequence, we can also add a leaf, make it adjacent to one of the vertices, right? And then we will get a tree in A, right? So it must be present in one of the AKs. So therefore, there is a one-to-one correspondence. So the cardinality of AK is precisely the cardinality of the trees that we obtain this way. Now the trees that we obtain this way is all trees, right, that we can get where the degree sequence is given here, right? All trees on n minus 1 vertices where the degree sequence is given here, right? D of Vi is equal to Di, I not equal to K, and degree of Pk is equal to Dk minus, right? So now we can use index, right? So what is the induction, right? So well, whatever is the number of vertices, right, which is n minus 1 in this case, minus 2, right? N minus 2 becomes n minus 1 minus 2 factorial. So we have n minus 3 factorial divided by, right, the degree sequence whatever it was given, that di minus 1 factorial etc. into each of them, right? So now here the degree, the first one is degree of Vk is dk minus 1, so that minus 1 which is dk minus 2 factorial. Then product over all the remaining terms, right, di minus 1 factorial for I not equal to j and k. Now this is just manipulation now, right? So this is the cardinality of AK, and now that is equal to n minus 3 factorial into dk minus 1, because I just multiply by dk minus 1 factorial and dk minus 1 on the above and below, right? So therefore this becomes dk minus 2 factorial into dk minus 1 becomes dk minus 1 factorial, which I can take inside, right? I can take it inside, and then the numerator at that time is remaining, right? So that then I will get n minus 3 factorial into dk minus 1 into product I not equal to j di minus 1 factorial. Now here is something that we should observe, that so I not equal to j, right? There is one term still missing from our general formula, but what is that term? That term is dj minus 1 factorial, right? But we know that dj is equal to 1, right? Degree of dj is dj, which is equal to 1. Because dj equal to 1, dj minus 1 factorial is 0 factorial, which is also 1. So I can as well put that term inside. Right? Doesn't make any difference because dj is 1. So then I can just write it product over all I di minus 1 factorial, because it doesn't matter whether I add that particular case of dj. So therefore I will get this without I equal to j, so I can even write it this way. Now, so what is the cardinality of A? Well, it is the sum over all k different from j, cardinality of AK, right? By definition here, right? It's the union over all k, AK. And what we have? Well, summation over all k not equal to j, summation, equal to j, n minus 3 factorial into dk minus 1 by product I not equal to j and di minus 1 factorial. Now, we can write this as we just mentioned in the previous slide, right? We can write the summation n minus 3 factorial into dk minus 1 by product over all I di minus 1 factorial. Now, since these terms are not depending on k, we can just take it out. So we get n minus 3 factorial by product over all I di minus 1 factorial. Summation k not equal to j dk minus 1. Now, what is this sum? Well, this is the sum of the degrees where k is different from j, and we can see that it is actually equal to n minus 2, right? So because we are basically saying that summation dk minus so summation dk is 2n minus 2, then we have like minus the 2n minus summation dk is k not equal to this. This is 2n minus 3 minus n minus 3 minus n minus 1, which will be n minus 2. Right? So this is equal to n minus 2 factorial by product dA minus n factorial. So this gives us the induction, and therefore we show that this formula is true by induction. Right? So the number of trees on the vertex at B1 to Bn, where degree of dA is equal to fixed number dA, is given by this, provided summation is going to be 2n minus 2. The degree sum should be equal to twice the number of vectors. Okay, so we have proved that. Now, since we have this, we can use this to find the number of all trees, okay, on Vk because for each degree sequence, now we know how to find it. So you can sum over all this thing, we can get the. So that is a homework for you, right? Show that the total number of trees on V1 to Vn is n raised to n minus 2 by using the above result, right? For a given degree sequence, we have this n minus 2 factorial by product dA minus 1 factorial. So that sum should be equal to n raised to n minus 2, right? So show this by using the previous. Now again, once we have this, we can immediately show that the number of rooted trees on the vertex at 1 to n is n power n minus 1. Okay, this is also immediate consequence. Once we have this, this is easy. Okay. Now let us look at so we will look at the remaining questions maybe later, or you can work out these details once you learn more sophisticated technique. So here we look at an introduction to graph coloring. So graph coloring is a very very useful subject. There are many. It's one of the major areas in graph theory nowadays. Okay, so because there are so many different versions of coloring, and each coloring can represent many different problems from real life, right? So there are so many kind of questions that arises, which can all be converted to graph coloring questions. So therefore, this has become a huge area. In fact, a major part of graph theory is now graph coloring. Okay. So I did my PhD in graph coloring, for example, during my PhD time, and there are many other related coloring notions. We will look at one for the time being, and maybe later we will look at another related notion. But there are dozens, or even in fact hundreds of coloring notions, and then we can add many constraints to the questions that we ask. So here is the general idea of coloring. So coloring is basically a fancy name for partitioning or right of the vertex set. Like so, given a simple graph G and let's say a set C, a coloring of G using the set C is a function from B to C. Okay, so that is all a coloring is. Now, a coloring is, so most of the time when we are going to use this. So a coloring is called a proper coloring. Okay, so a coloring F is called a proper coloring if it gives different colors to adjacent vertices. Okay, so if U and V are adjacent in the graph, then F of U must be different from F of V. Right? In that case, the coloring is proper. Otherwise, the coloring is not proper. So even if it is not proper, there are applications for that. But most questions will look at proper coloring. We will see many versions of proper coloring we will look at. So basically, vertex coloring is what we immediately when we say graph coloring, it is the first thing is the vertex coloring. Right? There are other notions of coloring, edge coloring, and face coloring. There are many things we can do, and These all depend on the cases, but when we say coloring, it is usually watercoloring. And most of the time, we will just write coloring to say that proper coloring of the vertex, where the adjacent vertices get different colors. Now, if we are using a coloring which is not proper, we will mention it that way. So, if I just say coloring without mentioning anywhere that we are not looking at proper coloring, it is assumed to be proper coloring. Okay, this is the convention that we make. So here are some examples. So we have a graph G with some colorings here. So let's say the set C is R, G, B, and K. Right. I am going to color using these four possible colors: red, green, blue, and black. Right. So what are the colorings possible? Like let's here is a proper coloring of G using the colors in C, where I color the central vertex with B. Right. Then these vertices cannot be colored B because I am looking at proper coloring. So this must be different from B. It has to be, let's say, G. This must be different from B and G because they are adjacent to each other. So therefore, this is all different three colors. But on the other hand, I can use G again here because these are not adjacent. Right? So I use the same three colors to color all the vertices. I don't even use the black color. Right? So with just three colors, I colored the entire vertices. It is a proper coloring. It uses only colors from C. So therefore, it is a C coloring of G. Right? Proper C coloring of G. Now here is another proper C coloring of G. Right? So I use the color black also. So K is used in the middle in this case. And then I use R and B here. I can either use R and B or G and R here. B and G here. Whatever I please. So I get another proper coloring. Here is another C coloring, but which is not proper, right? So I use color B here, I use B and G here, and I use G and K here. But now I use R and R here, but R and R are adjacent. Therefore, it is not a proper coloring, but it is a C color. So we have this kind of all kind of colorings we can look and see which are the ones which are proper. And then we can ask, can we count the number of proper colorings? We can ask what is the minimum number of colors that will give you a proper coloring. So these are the interesting questions we will look at in graph coloring. So again, as I mentioned before, unless stated otherwise, when I write coloring, it is proper. Now, the smallest integer, right? That is the cardinality of a set C, such that the graph G admits a proper C coloring is called the chromatic number of the graph G. It is denoted by chi of G. So the chromatic number is the smallest number of colors that will allow a proper color. Right? For example, let's say that I take this graph. Okay? Or maybe this graph. Okay? Now, what is the minimum number of colors that will allow to color this graph? Okay? Suppose I how do I argue this, right? Suppose I start with color 1, 2, 3, 4, etc. so that I can use the minimum number. So I start with the color 1. Okay? So I color this vertex with 1. Now I know that because I colored this with 1, I cannot use color 1 here, right? So it must be different from 1. So therefore I can give this 2. Right? Now there is a question whether I want to use color 2 here or I want to use a new color here. I don't know which is the best, but for the time being, I will say that okay, I can reuse the color because I want to minimize, right? So let me say that I am only using 2 colors. So then in that case, I have to use 2 here, right? Because I cannot use 1. So I can safely assume that I am using color 2 here. Now since I have used color 1 here and color 2 here, I cannot use color 2 here. I am using only 2 colors. I have to use one more. I mean, I have to use the color 1 here because I cannot use color 2. Now because this is 1 and this is 2, right? So because this is 2, well, here it is 1 and it is 2. I cannot use 2 here. So I have to use maybe 1. But I cannot use 1 here because I have already used 1 here. Right? So therefore, we know that we need to use at least one more color. So we need 3 colors to give a proper color, right? So the number 3 one can convince that is minimum required, and because there is a coloring with 3 colors, we see that it is a chromatic number of this graph. Right? So we showed that less than 2 is not possible. I mean less than 3 is not possible, and 3 is possible. So therefore, that shows that there is a coloring with 3, and that is the smallest. So we get 3 to be the chromatic number of this graph. So this question is like, can we find the minimum number that is required, right? That is for an arbitrary graph that I give you. While we are not going to really discuss this, one can show that this question is not an easy question, and in fact, if you want to find the value algorithmically, then it is a question that is not known to have any polynomial. I mean, it's not known to have any polynomial time algorithm. So it's an NP hard question, and we still don't know whether we can solve it in polynomial time. So it's going to be a difficult question to actually find the smallest number, right? To be the precise number for general graphs. Now there could be several graphs, classes of graphs where we can easily find it. That we will discuss usually in a graph theory course. But in this case, maybe we will not look much into it, except we will look at some bounds. So what we are going to look at is, can we say that what is the smallest number which is which is necessary? The largest number that you can say is necessary, and the smallest number that will suffice. So we will get a lower bound and upper bound, and then we will get to reduce the gap between these and see how much close we can go without spending too much effort. So this is another interesting direction. So there are many questions one can come up with and many other parameters, but yeah. But I just wanted to point out that finding a minimum makes sense. We will see some examples of applications for this. Now here is a graph. What is the chromatic number? Let's see what is the smallest. So can you find out what is the minimum number of colors required for this? Okay. So one thing that you can immediately say is that if the graph has at least one edge, you need at least 2 colors, right? Without, if there is an edge, the endpoints must get different colors, right? So this is clear. So therefore, if the graph is a non-empty graph, then we will need at least two okay. So now the question is that what is the minimum that will suffice, right? So in this case, one can show that 2 is sufficient, right? So what I am going to do is that, let me start with vertex here. Let's say color 1, or maybe I will use another. Okay, color 1. Now let me take another vertex, right? So let us say that I take the vertex which is neighboring this, right? Neighboring this vertex. This is going to get color 2 because I cannot give the same color. But now I see that these neighbors of these 2 can all be given color 1 because there is no edge connecting. Therefore, this all I can give 1. Now I can give color 2 to here, and therefore I get a 2 color. So because 2 is necessary, we see that this is equal to 2. Right? The chromatic number of the graph is equal to 2. And we might should improve. Right? Okay. Now what about this graph? Right? So the graph H, what is the chromatic number? Well, we can try using some method. Now let's say that I start with color 1 here. Now I can color this with color 2, right? Then I know that I will need color 3 here because I cannot use color 1 or 2 here. And now here, right? Here I can use either I can use only 2 because 1 and 3 are not possible. So therefore I use color 2. And here I will use color 1 again, right? So I can do with color 3 colors, and since I can see that at least 3 is required, right, from this part, because all these 3 are adjacent to each other, so therefore I have to give different colors to each of them. Right? So therefore I will say that this requires at least 3. So this is equal to 3. Now, one of the observations that we made during this is that, like, if 2 vertices are adjacent, they must get different colors. So if all the vertices are adjacent, all of them must get different colors. So chromatic number of the complete graph on n vertices must use at least n different colors, right? Every vertex must use a different color. So this is actually equal to n, right? So the chromatic number of the complete graph is the number of vertices, because every vertex gets a different. Now, here is an observation that we actually observed in the previous examples, that the chromatic number of a graph is at least the smallest complete subgraph which is sitting inside. So if there is a complete graph sitting inside, all of the vertices must get different colors, and omega is the cardinality of the smallest, the largest complete graph, not smallest, the largest complete graph sitting inside. Okay, so omega is the largest complete graph sitting inside. So omega of G is the cardinality or order of the largest complete graph, right? Complete subgraph. So chromatic number is at least the omega of G. Right? So this is called the clique number. So this kind of complete graphs which are subgraphs are called cliques in a graph. So clique. So the clique number is small omega of G. So the chromatic number is at least the clique number. That is immediate because we know that all the vertices of the clique must get different colors. So we get immediately we got a lower bound, right? So we know that it must be at least omega for a lower bound for chromatic. Now we can think about upper bounds. Can we say that, okay, omega is always less than or equal to, chi is always less than or equal to something, right? Can we say chi of G is less than or equal to something? Of course, the immediate thing that you can say is that it is less than or equal to the total number of vertices, right? But it is a useless bound because we know that it is, we cannot even give more colors anyway. Therefore, this is a trivial bound which is not very useful for us. So now the question is that what can we say about a number which is different from it, right? Can we say still that it is less than or equal to something? So maybe you think about this for a few minutes, right, and come up with a number. That then we can go ahead, right? So let us look at something. Okay. Now, before going into an upper bound, let us look at one application of coloring. So here are some students clubs, right? Student clubs, and there are a number of them, and they want to plan monthly meetings schedule. Okay. So every month they are allotted a weekend, right? On Sunday, let's say, you can arrange your meetings on this day. Now the problem is that, like, if when a student belongs to 2 clubs, and if both clubs are meeting at the same time, right, then this person cannot attend both the meetings. but of course I don't want to miss the club meeting, right? And therefore, what you can do, right? So you want to find out we have to make sure that when we assign the or decide the time schedules, we have to make sure that they don't intersect, right? So how many different slots are required? Right. Now, of course, if every club has a different slot, that will be required. But if the number of clubs is large, maybe we don't want to spend too many hours for this, right? Maybe we have more than 10 clubs, and then maybe we will find out that we don't want to spend 10 hours in a Sunday for this. So let us try to see what is the smallest number possible. So can we do it less than the number of clubs? So of course, this is the question. We can design as a graph coloring question. So how do you design it as a graph coloring? So each club, let's say, becomes a vertex of the graph. Okay. So this is club 1, then club 2, club 3, club 4, etc. Right. So we write these clubs as vertices. Right. So we get several of these clubs and the several of these vertices. Now each vertex, so now I have to define the graph, which means that I have to define the edges. So what are the definition of edges? So the edges are there between two clubs if the clubs share some member. Okay. So if the club 1 and club 2 have some common member, then I put an edge between. When if there is at least one member in common, I put an edge between. Then I define the graph like this, right? So whatever is there, I will say that okay, these are the relations, right? So once I have this graph, I say that if I find the chromatic number of the graph, that tells me the least number of slots that will work for doing this club meeting schedules. So how do you do that? Well, let us say that each each slot is given some numbers, right? 1 to k, right? Each slot is now a color. Right? Numbers can be colors because our sets elements of sets are colors. Right? So now what I am going to do is that I am going to color the vertices in a proper manner with the least number of colors possible, right? So therefore, if I start coloring, let's say one of these clubs with color 1, right? I mean, not like this actually, I want to find the minimum, and this procedure will not tell me the minimum, but no, just to give you a flavor. So let's say that this vertex is given color 1, then I know immediately that okay, because C2 is adjacent to C3, C2 cannot get color 1. So it has to use a different slot, let's say 2, right? Now C3 and C2 are adjacent to C4, so therefore C4 must not because they have common members, so therefore I need to find a different slot for C4 also. Right? So this way, the coloring will give you a schedule, and if you find the minimum number of colors, that will give you the minimum number of slots required for the meeting schedule. Okay, something if you think about a few minutes will be much more clear to you. Okay, so yeah, I think this is the same thing that I was mentioning. So finding the chromatic number of the graph will tell you, will help you to resolve this. Now, here is an observation about the upper bound. So if G is a simple graph, then the chromatic number of G is at most the maximum degree of G plus 1. Okay. So given any graph G, so the delta of G is the maximum degree, right? The degree of vertices are there, T1 to Dn, and then the maximum among the degrees is called the maximum degree delta. This is something we defined earlier. So whatever is the maximum largest degree in the graph, that plus 1 is an upper bound for the chromatic. So can you see why? Okay. Maybe you should think about this for a few minutes. Figure out why this is an upper bound. Okay, so here is the reason. So I just take the graph and then start coloring. Okay. So what I am going to do is that I pick a vertex, whatever vertex I want, which is not colored, and try to give it a color. Now when I am going to take this graph, pick a vertex, right, and then I am going to color this vertex with some color, right. So let us say that the degree of the vertex is let's say D, right. So the vertex is U and the degree is D. Right? Now, if the degree of the vertex is D, I am going to pick. I have already picked this vertex, and now I want to color with some color. Right? So I want to associate some color to this vertex. So what are the colors that I cannot give to the vertex U? Right? I cannot give a color to U only if that color is used in one of its neighbors, right? Either here or here or here. Right? So you look at all possible D neighbors. Each of them can use at most one color, and in total it can use at most D colors. Right? So if I have more than D colors available in the set, right, in C, if I have more than D colors, then I can use one of the colors other than this D color, right? This could be less than D, but at most D, right? So one of the colors other than this D will be available, and that color I can use here. So if I have at least D plus 1 colors in the set, I can always color the vertex with degree D. Now this is true for any vertex, right? No matter what the previous vertices are colored with, this vertex can always be colored with if I have at least D plus 1 colors available. Now delta is the largest such D, right? The maximum. So we are looking at maximum over all D, right? Degree of all D of U, right? Maximum over all U, D of U, right? Maximum over all U, all the vertices, D of U, right? That is delta, and therefore D is going to be less than or equal to delta for every vertex, right? Du is going to be less than or equal to delta. So when I'm taking delta plus 1 colors, right, I have at least one color available even if I use all the delta neighbors with different colors. So therefore I say that I can always color with delta plus 1. So the chromatic number is less than or equal to delta of G plus 1. This is immediately clear. Now once you have something like this, okay? So in graph theory, like the questions that we come up with are like this. Suppose you have inequality. Then the first question you can ask is that when is the inequality actual inequality? Is it ever attained? Is it possible to get a graph where you actually need delta of G plus 1, right? Or is it possible to do with less than delta G plus 1 if the graph is, let's say, not one of some specific graphs, right? Or in all cases. So these kind of questions are interesting. So, so what is this question that we ask immediately is that precisely which cases can attain this bound as equality. And then if the equality is not attained, then what can you say about the other graphs, right? And what is the largest bound then, and things like that. So this is solved by a very famous theorem called Brooks theorem. Okay. So Brooks theorem says that there are only two classes of graphs which require delta of G plus 1. Okay. So the first one is what is called the odd cycles. It's odd length cycles are the cycle graphs where the number of vertices is odd. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so let us take an odd length cycle. Now the odd length cycle has all the vertices have degree exactly right? So the maximum degree is also equal to 2. But it requires 3 colors because, as we observed in the case of C5 earlier, if I start with 1 color, then I am forced to give colors 2 to these 2 guys if I am using at most 2 colors. Therefore, consequently, we have to use color 1 here and here, and then I started with color 1 here and here, and then I have to use color 2 here, right? But but I cannot use color 2 here and here because they are adjacent. So I need to use a third color. So these were all forced. Then we can say that this is the minimum. So for odd cycles, we can immediately see that we need 3 colors. Right? So what are the other graphs which requires delta plus 1? So it turns out that the other graph which require delta plus 1 are the complete graphs K. Okay. So if the graph is complete, we said that all the vertices must get different colors, right? So you take any complete graph, we know that every vertex must get a different color because they are all adjacent. But what is the degree? The degree is the number of vertices minus 1. So the delta is actually n minus 1, but we need n colors, so therefore it's actually equal to delta. So when the graph is a complete graph, Kn, or it is an odd cycle, C2n plus 1, we need delta plus 1 colors. Okay. So G not equal to C2k plus 1 and Kn, right? Then the chromatic number of G is less than or equal to delta of G, right? We don't want a plus 1. So this is something which we need to prove. Okay, this is just a claim. This is called Brooks theorem, and I will give this to you as an exercise to work out. It takes a little bit of work, but it will be very interesting. So so the question is that when is equality attained? When is K of G is equal to delta G plus 1? So equality is, as we mentioned, is when the graph is complete graph odd cycle. So what I want you to show is to prove the following Brooks theorem. If G is neither complete graph nor an odd cycle, then the chromatic number of G is at most delta of, which is the maximum degree. Okay. So what we have observed this much so far is that there is a lower bound that we found, which is omega of G, the click number, and an upper bound which we found, which is the delta of G plus 1, which is the upper bound for the chromatic number, right? So the chromatic number is between these two. Now we can ask many questions, right? When is this lower bound attained? This is an interesting question. There are several classes that we know attain this, but we still don't know universally when. Then can chi be much larger than omega of G? Okay. I mean, like so we know that the clicks will make the chromatic number large, right? If you have a large click with let's say t vertices, then we need at least t colors. Right? Now, can you have t to be small, right? The complete graph omega to be small, and then make the chromatic number much larger than omega, right? The click size. So because in the case of odd cycles, right, the delta is just 2, right? And, but that doesn't say that for very large numbers, chromatic numbers, we can have this property. But is it possible? So here is an interesting result, which says that we can have graph without triangles, okay, where the chromatic number is as large as we want. What do you mean by triangle? Triangle is 3 vertices which are adjacent to each other, which is the complete graph on 3 vertices. Now, if I have several vertices, and if there is no triangle, then I cannot have any complete graph more than complete graph on 2 vertices, an edge, right? Because if you have any larger complete graph, every vertices are adjacent, so therefore you will automatically get a triangle as a subgraph. So when there is no triangle, we know that the click number omega is going to be 2, right? So what we are saying is that we have graph with omega is equal to 2 and chromatic number as large as you want. And how do you do that? Okay. So of course there are many ways to do this, but one famous result was this construction that is given by Misersky. Okay. So Misersky constructions shows that if you are given a graph which does not contain triangles and has some chromatic number, let's say k, then I can make a graph from this graph, right, a new graph whose chromatic number is strictly larger than k. In fact, it's equal to k plus 1, and there is still no triangle. So I start with a triangle-free graph. I make a new graph. The chromatic number increases by 1 without creating triangle. So therefore, I can keep on doing this. So I can make the chromatic number larger and larger. So what is the procedure? So the procedure is the following. Okay. So given the graph, so here is a small example, right? So given this graph, I take the graph and keep it as it is, one copy. Okay. So I keep the copy of the graph as it is. Now I make a duplicate of every vertex. Okay. So duplicate of vertex means that so there is a copy of V1, right, which I call U1. There is a copy of V2, which I call U2, etc. So I make these copies of this graphs, and then I make, the neighbors of U1 are precisely the neighbors of V1. Okay, so V1 had the neighbor V2, so therefore U1 has the neighbor V2. Right? U2 had neighbor, V2 had neighbor V1, therefore U2 has neighbor V1. Whatever is the neighbor of V1 in the graph G, that same vertices are going to be the neighbors of the corresponding vertex here also. Okay. So now whatever graph I get from here, finally I am going to add a new vertex that is called W, and W is adjacent to all the new vertices that I introduce. Whatever is the number of vertices here, I am going to make W adjacent to each of them. Okay. Now UIs form an independent set, right? That is immediately clear because you can see that UIs, there is no edge between them because they were not neighbors of any of these vertices, right, before, right, in the graph, in this graph. So therefore they form an independent set. So when I add W to these guys, this is not going to create any triangle because if it creates a triangle, there must be some edge here. Now similarly, there was no triangle in this graph. So now there is no triangle here. Now can this create a triangle, right? Now U1 is adjacent to all the neighbors which were copies of, the neighbors of V1, right? So if I look at the graph with just U1, this U1 cannot be part of any triangle because U1 is precisely like V1 in the graph, right? If I look at just the graph V with the addition of U1, if there is a triangle involving U1, there is a triangle also involving V1 because that is the triangle in this graph only, right? Any triangle here is also a triangle here. So this is true for every single vertex, and because there is no edge here, we don't have to look at two of them together, and therefore I show that this graph is triangle. Right? So I get a triangle-free graph by doing this, and then now I want to show that the chromatic number also has increased by 1. Right? Now, how do you show this? To show that the chromatic number is increased by 1, we have to first show that there is a coloring with one more color, and we have to show that there is no coloring with the chromatic number of G many colors. Okay. So how do I do that? So here is an idea. Let us first show that with K plus 1 colors the coloring is possible. That is easy, right? Because I start with a coloring of the graph G, right? The first graph that I started with. Now, whatever is the coloring here, each vertex, let's say Vi has some color, I use the same color to color Ui also. Now, because there is no edge between Ui and Vi, I can give the same color here, no problem. And this color, of course, is okay to give because this vertex is adjacent to only the neighbors of V1. And V1, I have given this color C. That's the color C, right? And because all the neighbors of V1 gets different colors, right? Other than C, all the neighbors of U1 also get a color difference. So therefore, U1 will not create any problem with the color. Right? So this I can do for any UI. So therefore, I will get I can use VI, the color of VI to be equal to the color of UI. So I get all these vertices, the same color that is happening here. And now for W, I give a new color, right? The whatever is the chromatic number plus 1, right? So one more color I give, and that new color is this. Now because it is a new color, it will not create any problem with any of the existing colors. And therefore, I get a proper coloring with one extra color. Now we want to show that by there is no coloring with chromatic number of G many colors, right? So let's say that chromatic number of the graph is K. Then I want to show that there is no K coloring, right? Of the new graph. Now, why there is no K coloring of this new graph? Suppose there is a K coloring. So we will start by assuming that there is a K coloring of this new graph. Now, suppose there is a K coloring of this new graph, then it uses this K colors, at most this K color is 1 to K, right, on the vertices. Now, given any coloring, okay, so this is one property of coloring, right? Given any coloring, let's say using, let's say color red, blue, green, etc. I can always change the names of the colors. I will say that all the red vertices now I am going to call as new green, okay, and all the green vertices in the original graph I am going to call as red, right? So I just change the names of red and blue to each other, right? So red is now the new blue, and blue is is the new green, and green is the new red. Right? So this is just renaming the colors. It does not affect anything about the properness of the color, right? Because earlier it was called red, now it is called blue, or green, whatever. So therefore, I can always change the names of the colors as far as I change uniformly everywhere, right? All the red I change to green, and all the green I change to red, right? Then it is okay. So therefore, we can assume without loss of generality that the vertex W is colored with the color K. Just to make the argument easier, we don't really have to assume, right? So we will assume that the vertex W is colored with the color K. Okay. So here is a better picture, I think. So we have this graph G and U1 to UN, and UI is adjacent to all the neighbors of VI also. So UI and VI are basically clones of it, exactly the same vertex, just one copy of VI. And UIs are independent, and then W is adjacent to all of the UI. So now, to show that there is no K coloring, I will assume without loss of penalty that W is with colored with color K. Now, because W is adjacent to all the UIs cannot be colored with color K. Right? So therefore, U1 to UN must be colored with colors 1 to K minus 1. Right? This must be the color that is used on UI, because K cannot be used on UI. Now, if 1 to k minus 1 is used on ui's, I claim that I can use the same 1 to k minus 1 to give a coloring of G also. Why is that? Because see, ui, whatever color is for ui, that is adjacent to the vertices here, right? So, the color of ui is not going to be used on the neighbors of vi, right? Because ui and vi share the same set of neighbors. So therefore, since ui is given some color, whatever color it is, that color can be given to vi also. Because the neighbors will use different colors, right? So this I can do for every ui, which means that the colors used here can be exactly used on the colors v1 to vn also. But this says that I am using, just the colors 1 to k minus 1 to color all the vertices of the graph G. But G was a graph with chromatic number k, which means that there is no k minus 1 proper color. So this contradiction proves that there is no coloring where only we are using k colors. So therefore the chromatic number is at least k plus 1. And we already proved that it is actually at most k plus 1. So therefore the chromatic number increases by exactly 1. So we get a graph from a triangle free graph. We get a new triangle free graph whose chromatic number increases by 1. Now I can start from this new triangle free graph and increase the chromatic number again by 1. So I can keep on doing this. So I get larger and larger chromatic number. So this is called the Michaelskian construction, and such graphs are called Michaelskian. So given a graph G, the Michaelskian of G is the graph we construct this way. Take the graph, make copies of each of the vertices, right? And which means that exactly the same numbers are in the graph G. And because this is the new independent set, I make it a new vertex adjacent to W, and then I will get this new graph, which is Michaelskian. So this is the construction. Okay. Now, there is another famous result of Paul and Girth, which says that we can have graphs with arbitrarily large girth and arbitrarily large chromatic. So what is the girth? So the girth of a graph is the length of the shortest cycle. Okay? Shortest cycle, right? So which says that it's not just triangles, right? We can make your cycle as large as you want. Okay, the smallest cycle is as large as you want. So there is not going to be any other edges connecting this, right? There cannot be an edge connecting this. It will become smaller. So you will have all the cycles be large enough, right, in the graph. So as large as you want, you can make the smallest cycle, and then you can make the girth, the chromatic number also as large as you want. Okay. So this is using probabilistic method. We will probably not discuss the proof, but we will learn at least some of the tools that is required to work out these details. So this is a very, very old result of Paul and very influential one. And you will see that this result, precisely this result that Herodot used, Herodot proved, was used to prove the addition, to come up with the proof for the headed name is this result was used to prove the headed name is condenser, right, that I mentioned sometime before, or maybe sorry, I will mention it soon. So yeah, so this is a very influential result and very famous result, and it has so many applications, like on existential graph theory. So where you show that you don't tell you how to come up with a graph like this, but it will tell you there must be some graphs with this property. Okay. Now a very important operation in graphs is called contraction of interest. So the definition is as follows. So given a graph G, it's a simple graph, and some edge, let's say u dash. Now what I do is that I take the graph G and delete the edge E. Okay, so just remove the edge G. Then identify the vertices U and U dash to make a new vertex. Let's say U star. So I am not doing anything to any other vertex, right? The adjacency remains the same for U. All the neighbors are going to be there except the one that we just removed, the edge, right? And for U dash, all the remaining neighbors are as it is. Now I basically identify this U and U dash, right? Which becomes a single vertex. So all the neighbors of U other than U dash will be there in the new graph. All the neighbors of U dash other than U will also be neighbors of this new vertex. So I will get this new graph. So this is called the contraction of the edge. Okay. So here are some examples. So I start with this graph, right? I start with this graph. Then I find the graph G minus E by removing this edge that we fixed. So E is the edge, which is C and C dash. So I remove the edge E, I get this graph. Now I identify C and C dash, which means that C and C dash become the vertex C star. The neighbors of C and C dash, right? C had the neighbor B, C dash had neighbor B. Right? They will be still neighbors. Then C also had neighbor A, C dash had neighbor A, so C star will have neighbor A also. So after contraction of this edge, I will get this graph G. I denote it by G right slash E. Okay, so this is one example. So here is another example. So I start from this graph. Right, I take the edge U dash as our edge to contract. So it means that I delete this edge. Now I identify U and U dash to U star. So of course the neighbors of U, which will be 4, neighbors of U1, which is 2 and 3, will be neighbors of this, and 4 and 1, and similarly 2 and 3 will be neighbors of U star. Right, remaining neighborhood remains as it is, right, and that's it. So you get G bar. So this is the contraction process. Now contraction is very important because we will not go into details of minutes. That a graph, you start with any graph G, and you can apply as many as deletions, contractions, or vertex deletions also possible if you want. Then you will get some kind of graph from the startup graph. So these graphs that you can obtain by any sequences of edge contractions, deletions, and vertex deletion are called minors of the graph. So there is a huge area called minor theory, right, which studies like to classify graph based on its minors, what are the properties. Many important results have improved using this. Okay, so there is a whole set of courses one can offer based on just minor theory, not one course, several courses. So it's a huge area, and I really have not looked much into minor theory, but it's a very interesting area with many applications. There are some few things we will see in a graph theory course in minor theory, like things like classification of planar graphs using its minors and things like that. So these things we will not discuss in this course. We can do this in an elective course on graph theory. So I will not discuss minors for the time being. I just define this so that we need this operation to look at something else. So what is that? So given a graph G, first thing that we said that what is the chromatic number, which is the minimum number of colors which which suffices to color the vertices of the graph such that adjacent vertices get different colors, right? Now another combinatorial question that one can ask is given a graph and let's say a set of colors. Let's say I tell you I am giving k colors because all the sets are like the sets of the same cardinality are the same for us. We can just assume that it is a set. Once you know the cardinality, you will just assume the numbers are from 1 to k are the colors, right? One number 1 to k are the colors. So given a graph G and a number K, I can ask how many K colorings, right? How many colors, how many different colorings of the graph are possible with using exactly K colors. Okay, so the number of K colorings of the graph G. Right? So this number is let's say chi of G comma K. Okay, so the graph G and is given, and then a number K is given, and the question is that what is the number of colorings of G using K colors. So for each K you can find this, and for general K you can write it as a function. So we can say this is a coloring function, right? If you assume K to be a variable, or like replace it by X, so then I will get the chromatic function of the graph. Okay. Eventually one can show that this function is always a polynomial, and therefore it is a chromatic polynomial. It is a nice exercise using some of the techniques that we learned, but let us not go into that. So given a graph G, we want to find out the number of colorings, right, proper colorings using exactly K colors. Now, my claim is that this parameter chi of G comma K satisfies this following identity. Okay, so given a graph G and any edge in the graph E, okay, we will assume that all our graphs are simple for the time being. Even otherwise, many of these things hold, but we will not work with that assumption. So, given a graph G and an arbitrary edge G, we say that the chromatic function or like the K colorings of G using which are proper is equal to the number of K colorings of G without the edge G, right, G minus E, minus number of K colorings of G contraction E. Okay. So like basically what it is saying is that the number of colorings of this graph, right, is equal to the number of K colorings of this graph is equal to number of K colorings of this graph minus the number of K colorings of this graph, right, using the same K colors, right? Similarly for any graph, right? So I want you to think about this and try to prove this identity as well. Okay, so why? So if you think about what is the proper coloring and what exactly happens when you take the contraction or edge deletion, you can immediately come up with this identity. It's not a difficult thing. Just you have to just think about what is meant by a proper coloring and what happens in G contraction E and what happens in G minus E, right? What is the difference between these two guys and what is the similarity between these two guys? Okay, so this will allow you to give a proof for this. Okay, so I think that is all we have for today, and we will look at a few more things in the next class, and then we will go to some other topics for this course.